All right, welcome everybody. So we are going to have our exam next week, either on Wednesday or Thursday. So I'm trying to figure out which day is best for us. I'll see if I can put out a poll or something so that we can decide. I can get some feedback from everybody. And it'll function just like the previous exams, just like the last exam, and it'll give you from, a large window of time to do it, because I know you have other finals coming up. It'll cover all the material. So we'll be reviewing that material this week. Today, I'm going to review Chapter 6 stuff. Since we just talked about that, I think it's worth going over again. And then Wednesday, Thursday, we can talk about the other material. So please come Wednesday, Thursday with questions. Okay? And next week, we won't have any classes. We'll just have that final exam on Thursday. But I'll be available to communicate over messaging and over email. Okay? So, the last homework's been posted in Chapter 6. Take a look at it now just to make sure it's there. Yep, section 6.4 has been posted. That's about Green's theorem. So what I want to do today is I want to go through Chapter 6 just kind of as a review, and we'll work out some practice problems that are similar to what you see in the homework. Okay. So let's do that. Let's review Chapter 6. So I'm going to take it over to the doc cam. Let me just adjust this thing here. Okay. All right, so Chapter 6, what we've been talking about. We started with Chapter 6, with section 6.1, and that was about vector fields. Okay, so vector fields are just a way of assigning a vector to each point in space. So at every point in space, we assign a vector, and a vector field in two-dimensional space would be given by two coordinates, because every point has two coordinates that define it. But you can also have vector fields in 3 dimensions, and so it'll have some function for its x coordinate and some function for its y coordinate. And these are functions of x and y because they have to have a function. They have to be valued at every point in space, right? And then we talked about line integrals in section 6.2. And line integrals came in 2 types. We first talked about scalar line integrals. And scalar line integrals, we imagined a curve, okay, and then we imagined a function who had a value at every point on this curve, right? Or maybe the function, maybe this curve is in the xy plane, right? And the function assigns a value to every point in xy. So it's a function of x and y. So its graph would live above the xy plane. And if you integrate this function along this curve, that's called a scalar line integral. And so that's going to, we would write it like this. How do we write this? We wrote f ds, right? And we evaluate it by doing the integral of f of r of t times the magnitude of r prime of t dt. And this is a vector function. So this is my curve over here. And what you're really doing there is you're finding the area of the the sheet that lies below the graph of f, but above this curve. So you see you get kind of a, if we look at all the points above this curve given by the height of the graph of f, we get this two-dimensional sheet. And this would represent the area of that sheet. Okay, so we're just integrating the function along the curve. The other type of line integral we talked about was a vector line integral. A vector line integral has to do with integrating through a vector field. Okay, so we're going to have a curve. So here's our R, and it's going through a vector field. So at every point in space, we have a vector. And the vector line integral will look like, the notation was f dot dr. Because what we're doing is that we're at every point on the curve, we're taking the tangent vector to the curve, r prime, and we're dotting it with the value of the vector field there. And we get a number, and then it turns into a scalar line integral. So the thing that we're integrating as a scalar line integral is the dot product of these two vectors. The tangent vector to the curve and the vector field itself. And so this is a dot product here. And when you write this out, it looks like this. So that's the vector line integral. And we use the vector line integral to compute work, which was given by just f dot dr. And we also talked about flux, which is given by f dot n ds, where n is the normal vector, the unit normal vector to the curve instead of the unit tangent vector. So it's doing the same thing, except instead of using this vector, we're dotting f with the unit normal. And so we talked about those things. And that was section 6.2. That's really the machinery that drives everything we're doing in chapter 6. Once you know how to do this, you can compute everything we need to compute. All right? So this is really all the computational stuff that we need to know. Okay? So what came next? Well, we came to section 6.3. Section 6.3 was about conservative vector fields and the fundamental theorem of line integrals. And conservative vector fields and the fundamental theorem for line integrals. All right. A vector field is conservative if it's the gradient of some function. Right? So a vector field is conservative if it's the gradient of some potential function. We call this the potential, if it exists. So some vector fields are conservative and some of them aren't. Sometimes you can't find this function. Sometimes it doesn't exist. And then we just say it's not conservative. Right? But if it is conservative, we have this great thing called the fundamental theorem for line integrals, FTLI, I'll call it. The fundamental theorem for line integrals says that, well, if you have a conservative vector field, then we can compute its integral in a very special way. So if I wanted to do the line integral f dot dr, this is just the value of its potential at the endpoints of the curve R. It's just the difference of those values. So I'm going to take f of R of B and subtract f of R of A. And like I said, f, where f is the potential for the vector field. So the fundamental theorem of line integrals only works when we have a conservative vector field. If the vector field isn't conservative, then you don't have this. You can't do it this way. You're going to have to do it the way we described on the last sheet, the way we defined how to compute the line integral in that manner. But if the vector field is conservative, if you can find this potential, then we can do the line integral much more easily. We can just use this. Just use the potential function. And that's fantastic, all right? And then we went into section 6.4. Section 6.4 was the last section we talked about. It's about Green's theorem. And Green's theorem is this great theorem that's similar to this, but instead of rewriting this as a difference between 2 points, we're actually going to integrate over an area and say that we can actually do that just by integrating along the boundary of the area. And I'm going to write it in reverse. I'm going to start with the boundary on the left. So there's a little bit of setup, and I didn't go into great detail on this last time when I talked about it. Let me be a little bit more careful in how I set this up. To state Green's theorem more precisely, let me write it out carefully here. If f, and suppose that it's given by P and Q, just like I said on the first sheet, these are the two functions that define the components of f. If this has continuous partial derivatives on a simply connected region, derivatives on a simply connected region, and call that region D, then simply connected means the region doesn't have any holes in it. All right, so like a region that would look like a donut has a hole in the center, right? Donuts have a hole, so that wouldn't be simply connected. But something like an apple doesn't have a hole. It's just one continuous blob, right? So it is simply connected. So as long as it doesn't have holes, it's called simply connected. Now, we need the vector field to have continuous partial derivatives throughout D. So that's something you should just check. Most of the vector fields we write down will satisfy that, but it's something to check. If it doesn't satisfy that, we don't have this theorem. But if all this is satisfied, then the integral of the line integral along the boundary, and I'm using this notation with a circle here. That means it's a closed curve, because the curve goes all the way around the boundary. So it begins where it ends. That integral around the boundary is the same as the integral throughout the interior of the region of this guy, qx minus py, the difference of the partial derivatives of these functions here. And what is C? C is the boundary of the region D, oriented counterclockwise. Okay, that's Green's theorem. The orientation of the curve matters because in that last picture that we drew here, I'm taking the dot product of r prime with the vector field when I do a line integral. Well, if the curve is going the other direction, then r prime points in the other direction. So I get the negative of the dot product. So depending on the orientation of the curve, I'll get either a positive or negative of the opposite orientation. So the orientation matters. It determines the sign of the result. Right? So that's why we specify the orientation of the curve here. So this theorem works this way, provided C is oriented counterclockwise. Sometimes to emphasize that, they put a little arrow here on the circle to say, hey, this is a counterclockwise curve. Right? So put a little arrow there. If you do it clockwise, it's the same thing. If you do it clockwise, it'll just become the negative of this. So instead of qx minus py, it'll be py minus qx. So it still works. So it doesn't have to be. So someone's asking, is it always counterclockwise? And the answer is no. I mean, you may be given a curve that's not counterclockwise, which means you can still do this, but you're going to get the negative of this answer. Or you'll do py minus qx instead of qx minus py. Or you could just re-parameterize your curve so that it is clockwise. You can rewrite the parameterization so it goes the other direction. And then you can use this just like it's stated. So it's not a big deal, but it is something that we need to state, okay?
Excuse me, can you hear me?
And that's Green's theorem, and that's everything that we talked about in chapter 6. Okay, so notice that these are kind of similar. Here we have the integral along a curve ends up being the difference of the points on the boundary of the curve. The boundary of the curve is just the endpoints of the curve. So I'm kind of evaluating this integral along a curve by evaluating at the endpoints of the curve. Same thing here. Here, to do the integral over a region, I'm just evaluating it on the boundary of the region, which is the curve. So it's a similar kind of picture going on here. I'm kind of reducing something over a larger thing to just going along its boundary. And that's something that, it's a theme that you'll see repeated again and again in calculus. And if we were to go further in chapter 6, you'd see that when we get to the divergence theorem and Stokes' theorem, they say the same kind of stuff, but for three-dimensional things, okay? That you can integrate throughout a three-dimensional region just by integrating along its boundary. And so that's something that is kind of really cool about calculus. So I want to do some examples here.
Excuse me, can you hear me?
Let's use Green's theorem to compute an integral. So let's move to a sheet. All right, which one should I start with? Okay, let's do this one. What we're going to do is we're going to do an integral along a curve. We're going to do f dot dr, okay, where f is the vector field, 2xy comma x plus y. There's my vector field. And what is c? Oh, I can't hear you. Oh, you know what? I'm sorry. You know what? My speakers might be turned off. Sorry about that. I did this last week once too. I might be able to hear you now if you're trying to use your mic.
Okay, can you hear me now?
Yes, I can. Sorry.
Okay. Sorry, I was just curious. What we were talking about these lines. Some of like how it's the formula is if it was counterclockwise, and if it was clockwise, it'd be reversed or it'd be the negative. But like what makes something clockwise or counterclockwise? I don't understand how a line could be like that. Describe it has to do with the,
yeah, so what makes it clockwise or counterclockwise? Well, it's the parameterization of the curve. Okay, so if I parameterize, if I write down the unit circle, if I imagine the unit circle, that's just an object, right? But I can come up with different parameterizations for it. So a parameterization is a way of specifying every point on that circle by a number. Okay, so the most common parameterization for the unit circle that we know of is cosine t comma sine t. And if you parameterize the unit circle that way, you will go around, I think looks right to you. I think of my image, I'm seeing a mirror image. So you go around counterclockwise. You go cosine t, sine t, right? So that's a counterclockwise parameterization. You could do a different parameterization of the unit circle. You could parameterize it cosine t minus sine t, and that will spin you around the unit circle in the clockwise direction. And so it all has to do with how we parameterize our curve.
Okay, so we basically have to, if we're just given the vectors, we have to kind of just imagine it in our mind, the graph, and use that to figure out if what we're being given is counterclockwise or clockwise.
You will be told. So if they say integrate along a curve, they should tell you whether it's clockwise.
Okay, so the problem should tell us
you won't be able to get the answer.
Okay, all right.
Say not enough information.
All right. Okay, thank you.
Although you could get the answer up to a sign. I mean, the answer is going to differ by plus or minus. So you could still do it and say, well, I know the answer is going to be either, this or it's negative. So you can still do it, but really the person didn't give you enough information if they didn't say whether you're going clockwise.
Okay. All right, thank you.
Sure. So let's go down. I'm going to describe the curve that we're integrating along here, and I'm going to do it just by drawing a picture of it. In the book and on the exercises, they give you a parameterization for the curve, but to be quick, I'm just going to draw a picture here. Okay, so my picture, if I can find my notes. Oh, here it is. Right, okay. So the curve that we're going to be dealing with is this guy. It starts at 0, 0, and it goes to 1, 1. And it starts by going along the graph of y equals x cubed. So that's y equals x cubed. So it goes this direction. Okay. And then it comes back from 1, 1 back to 0, 0. So then it's going to come back on a straight line. So that straight line is the line y equals x. So there, I've described the curve in a picture. In the book, they actually just said what I said in words, right? And you can figure that out. And the way they describe it, you could see here that it's counterclockwise, because we start at 0, 0, we go to 1, 1 along this curve, and then we come back along this straight line. That is counterclockwise. Okay. So we want to do this integral, and we can use Green's theorem for this. Right? These have continuous partial derivatives. Right? They're polynomials, so they have they're differentiable, and the derivatives are continuous. This is a simply connected region. Doesn't have any holes in the middle, so we can use Green's theorem here. And Green's theorem says that this integral is the integral over the interior of this thing, over the region D, of qx minus py. Well, this is p, this is q. Qx is the partial derivative of q with respect to x, so that's 1. Py is the partial of this with respect to y, so that's 2x. So that's what Green's theorem tells us. I hope. Maybe I didn't, I don't think I'm on the, am I not on the paper? I feel like I may not be. Let me, sorry about that. If I ever am not showing you the paper and it seems like I should, please chime in, let me know. Raise your hand, use the raise hand feature, or send me a chat, because I think I was not showing this. Let me go through it again so I can describe. We went up along y equals x cubed, right? This is the curve. We went back along y equals x. All right, so this describes a curve oriented counterclockwise. And what we want to do is we want to do this line integral, okay, which becomes, according to Green's theorem, a double integral. And the double integral that we do is qx minus py. Okay. Well, what are those? Well, this is the vector field is given by p comma q. So qx is the derivative of this with respect to x. That's 1. Py is the derivative of this with respect to y. So that's 2x. Right, so this is what Green's theorem says. We integrate along this, over this region now. Okay. So how do I do that? Well, we know how to set up double integrals, right? It looks like for every x between 0 and 1, y is going to go from here to here. So y is going to go from x cubed to x. There we go. So this is the double integral written out. So let's do this interior integral. Okay, well, we find an antiderivative, and we're integrating with respect to y, so it's going to be y minus 2xy, and we're evaluating from x cubed to x. So first I'm going to plug in x for y, and I get the x minus 2x squared. And then I subtract what I get when I plug in x cubed for y. So that's minus x cubed, and then I'm subtracting, so that becomes a plus 2x to the 4th. Okay? And now we are just doing this calculus 1 problem. There's this integral here with respect to x. So that's going to be, just find the antiderivatives. And then evaluate it from 0 to 1. Well, when I plug in 0, I just get 0. So that's nothing. I just have to plug in 1 here. So I'm going to get 1/2 minus 2/3 minus 1/4 plus 2/5. Well, that's 30 over 60 is a half, minus 40 over 60, minus 15 over 60, right, plus 24 over 60. Just getting a common denominator, that's all. So 30 minus 40 is negative 10, minus 15 is negative 25, plus 24 is negative 1. So I just have, my final answer is negative 1 over 60. Right. So there, we did this line integral using Green's theorem. We turned it into an integral over a region. Now you could have done it using what we learned in section 6.2, just as a line integral. We could have done it that way. And we would have used this formulation instead. And that would have gotten us the same answer. Okay, that would have worked. But this is how we use Green's theorem to do it. And when you can use Green's theorem is usually quicker. But it depends on the problem. Okay. So I'm going to be right back. I'm going to get a sheet of paper, some more paper. We'll do another example. Okay, so next up, we are going to do another one very similar to that one. Okay. And what do we got? We've got, I'm going to write it down in a slightly different notation, a notation that we haven't seen before. But I'll explain what this means. We're going to do an integral minus y dx plus x dy. And we're integrating along a curve where C is this curve, all right? So C is going to be, we're just going to integrate from the point -1, 0. We're not integrate, we're just going along a curve. Well, we are integrating, this is an integral. What am I saying? Yeah, we're going to integrate along this curve from -1, 0 to 1, 0. So it's just a straight line, pretty simple. And then we're going to come back along the top half of a circle. Okay, so this is a circle here. And I've oriented it counterclockwise. Went this way and then up back this way. So we're just going across this semicircle. Now, what is this notation? What does all this mean? Well, let's just go to a little thought cloud here, just off to the side. Remember what we've got is we've got F equals PQ, right? We're thinking of our vector field as one function, comma, another function, okay? R, the curve, can be thought of as a function of x, which is a function of t, and y, which is a function of t. Because every point here is has an x and a y coordinate. So they're both functions of t. So you can think of r like this. So when I do dr, I have dx and comma dy. If I take dr, I get this. So if I take f dot, and I should have a little arrow here, f dot dr, which is how we usually write down how we've been writing down our line integral up till now. Well, I'm just going to take this and dot it with this, right? So I got p dx plus q dy. Okay, so this is another way to write down the integrand of a line integral. And that's what we have up here. So I can see that this is my P and this is my Q. So in other words, my vector field here is just -y, comma x. Okay, so this is just another notation for writing down line integrals. So you'll see this in the homework. But you just remember that it's the same. It's the same as this. It's just a different way of writing it down. Instead of writing d dot dr, we will use a dx and a dy, because dr can be written like this. Okay, so how do we do this? Well, we're going to use Green's theorem, right? Because this is f dot dr, so we can use Green's theorem on there. So we're going to, Green's theorem says that that is the same as integrating over the interior here, this region. Call that D. Integrating what? Well, it's qx minus py. So it's the derivative of this with respect to x, that's 1, minus the derivative of this with respect to y, which is -1. So 1 minus -1 is 2. So Green's theorem tells us that this line integral becomes this area integral. Now this area integral is super simple. Whenever you're dealing with something like a circle, you should stop immediately and just think, is there an easier way to do this, right? I mean, all I have here is a constant, right? So if I pull that constant out, I have this. This is just integrating the function 1, right? Which gives me the area of the region. Now, once I know that, I know the answer, right? Because I know how to find the area of half a circle. The area of a whole circle is pi r squared. The area of half the circle is pi r squared over 2. Right? But we know what r is. This is a circle of radius 1. So the area is really just pi over 2. So that makes this super simple because that's what this is, right? So this is just 2 times pi over 2. So the answer is pi. So that one was super, super nice. Okay. And I want to do another one here. I want to do it in reverse. Okay, so we're going to use Green's theorem the other way around. We're going to start with the d integral, and we're going to turn it back into the line integral and do it that way. So let me see if I can find problem here. Okay, there's one in the book. It says, find the region bounded by the hypocycloid. Find the area of the region bounded by the hypocycloid, and then they give the formula for it, okay? So let's do that. Find the area of the region bounded by the hypocycloid, and that is given by cosine cubed of t, comma, sine cubed of t. They read it like this. What is that thing? Cosine cubed t, comma, sine cubed t, or using ij components, we could write it as a sum like this. Let's go take a look at it in Desmos. Okay, I'll share my screen here. Should be seeing that. And I plotted it over here in Desmos. Okay, so this is what it looks like. If I let t, I look at different values of t, you can see it starts out by coming up this direction, and then it comes up to, comes up to here by the time t equals pi over 2. And then when t approaches pi, it comes back down to here. And then when t is 3 pi over 2, we come around to this point. And by the time we come all the way to 2 pi, we've made our way all the way around this hypercycloid. So we want to find the area on the inside of this. Okay. So let's orient it counterclockwise. Well, actually no, it has its own orientation because it's given by an expression here. And you can see that as I increased t, we did move around this thing counterclockwise. Right? As I increased t, we were moving in the counterclockwise direction. So Green's theorem will work as it was stated. Okay. So just by the nature of this parameterization, it is counterclockwise. Going up this way, down this way, over here, and then back up by the time we get to 2 pi. Okay, so we want to find the area. So we're starting with this. We're starting with a double integral of 1 dA. That's the area. Now Green's theorem says that that's equal to the integral along the boundary of qx minus, of f dot dr. Okay? This is where the qx minus py is. In Green's theorem, the qx minus py is the thing we're integrating over the region, right? So this thing is supposed to be qx minus py. that will enable us to find the vector field, because whatever vector field it is, it has to be such that its x derivative of its y component minus the y derivative of its x component must equal 1. Okay? So can we think of a vector field so that, can I think of a vector field vector field PQ such that this is true, such that QX minus PY is equal to 1. Am I not on my screen again? Oh, thank you. I'm sorry about that. Oh boy. Okay, let me go through that again. Thanks for letting me know. So here we are. Here's the picture of the hypercycloid. We're going around counterclockwise, as we saw in Desmos, right? So the region here that we're finding the area of, let's call that D. And so the area is given by integrating 1 with respect to the area. And that is equal to, according to Green's theorem, that is equal to the integral of f dot dr. Right? That's what Green's theorem said. We just had it written down the other way. Right? Now, Green's theorem said that the integral of f dot dr was equal to qx minus py, right? So this must be qx minus py. In other words, qx minus py must be equal to 1. So what we have to do is find a vector field, PQ, such that qx minus py is equal to 1. That way, this will match Green's theorem. So as long as the vector field satisfies this, then Green's theorem says this thing would equal this. Okay. So can I find a p and a q so that qx minus py is equal to 1? Well, let's see. If qx is equal to 1/2 and px is equal to, sorry, py is equal to negative 1/2, then it works, right? 1/2 minus negative 1/2 is 1. Well, if qx is 1/2, that means that q must have equaled x over 2 plus a constant, all right? But I'll write the constant, but we're going to make it 0 to make things easy, all right? Py equals negative 1/2, so p must have equaled negative y over 2 plus some other constant. It doesn't, all we need to do is have a vector field that has these derivatives. So I'll just make these constants equal to 0, okay? You could do it with other constants there, it doesn't matter, but let's pick the easiest ones we can. So now we have a vector field that does satisfy this. We're going to use negative y over 2 comma x over 2. And now Green's theorem says that if I do this integral over the boundary, that's equal to this. Because now qx minus py is the same as this. So now Green's theorem tells us that these two things are equal. So I can do this now going the other way. I can evaluate the area by doing this line integral. Okay? So how do we do the line integral? Well, that's what we talked about in section 6.2. Okay? So to do a line integral, so let me write this out in fully so we can have see everything on this sheet. We're doing this, right? We're integrating the area. we said that's the same as the integral f dot dr. Okay. How do we do this? We take the vector field and we dot it with r prime of t dt. So we're going to go, let me write it like this. F of r of t dotted with r prime of t dt. And we're going to evaluate it from a to b. Now, to get all the way around that cycloid, we went from 0 to 2 pi. Okay. So now we need to find r prime of t. All right. Well, r of t was, what was it? Cosine cubed comma sine cubed. So r prime of t is 3 cosine squared t, and then take the derivative of cosine, which is negative sine t. And then the derivative of this is 3 sine squared t cosine t. Okay? So now we're going to evaluate f at r of t. So remember what f was. F was the vector, oh, what did we do? We did negative y over 2, I think, and x over 2. So because we just need qx minus py to be 1. Yeah, that'll work. Is that the one we did? There's more than one you can use here. That's why just checking. Okay. So f of r of t, I'm going to plug these things into here. All right. So f of r of t is going to be negative y over 2. So negative sine cubed t over 2. Comma x over 2. So that's cosine cubed t over 2. Dotted with r prime of t. So dotted with this stuff. I'm not going to write all that down here. I'll just write r prime of t dt. So now we take the dot product, right? So let's dot these. So we get this thing dotted with, multiplied by this. So we get 3 halves cosine squared of t sine to the 4th t. And then plus this times this, right? So I'm going to have 3 halves again, cosine to the 4th t, and sine squared t. Okay. Okay, so now it's a single variable calculus problem. We just have to do this integral. Let's see here. I'm seeing sine squareds and cosine squareds. I think that might be something we can simplify, right? Because we know this, so we know what sine squared plus cosine squared is. So can we get at that? Well, let's factor out some stuff. I know I can factor out the constant here. 3 halves is going to come on the outside of my integral. So that's nice. Each of these has a factor of cosine squared in it, and each of them has a factor of sine squared in it. So I can factor out cosine squared t sine squared t. And what's left over? Well, if I factor out of the first term, I'm left with sine squared t. And if I factor out of the second term, I'm left with cosine squared t. Oh, very nice, because I know this thing is equal to 1. So I've reduced my integral to this thing. Okay, so now it's a matter of evaluating this integral, okay? Let's see here. This one, I'm not sure what to do next. I think we'd have to start trying different things here. Integration by parts might be useful. Trig identities might be useful. Let me go take a peek at some trig identities, see if anything pops out. If you see anything that looks useful, yeah, I think there's a trig identity here that might work for us. There's a trig identity that says sine of 2t is the same as 2 sine t cosine t. Okay, that's a trig identity. So here I have sine t cosine t. So, and it's squared. So I can write this as, if I just divide both sides by 2 and square both sides, right, I get sine squared of 2t divided by 4. And what can we do with that? Well, I think there's another trick. So let's pull the 1/4 out. I think you saw some homework problems where you had to integrate something like this in chapter 5, right? And we used another trig identity. There's one that, another half angle formula. Sine squared t is equal to cosine 2t, sorry, 1 minus cosine 2t over 2, right? So this is the same as, let me write down the trig identity by itself. Sine squared, let me write down, sine squared of theta is equal to 1 minus cosine of 2 theta over 2. I'm slowing down because it's written in a different form, so I'm solving it in my head. Yeah. There we go. So we can use this one in here because I can turn sine squared into something like this. So instead of sine squared of 2t, I'm going to write 1 minus cosine of 2 times 2t, so 1 minus cosine of 4t. Okay, let's pull the 1/2 out. So this is going to have a 1/2 in it. The 1/2 is going to come out and make this 3 over 16, right? And then what's left is the 1 minus cosine of 2 times 2t. So that's cosine of 4t. Okay. Now that's not too bad. That is something that we can anti-differentiate, right? So I can anti-differentiate the 1 and get a t, and the cosine, I get a minus 1/4 sine of 4t. And we're going to evaluate this whole thing from 0 to 2 pi. Right? Let me just double check that, look it over. Looks okay to me. Okay, evaluating sine of 4t from 0 to 2 pi. I think if you know about the graph of the sine function, you know that's going to come out to 0, right? Or integrating this, you know, cosine 4t, we could have seen it right there. When I integrate this, I get 0. But yeah, like sine of, if I plug in 2 pi, that's sine of 8 pi, that's 0. When I plug in 0, that's 0 again. So this term doesn't matter. I'm just evaluating t from 0 to 2 pi, so that's just 2 pi, right? So that's 6 pi over 16, which simplifies to 3 pi over 8. Right. Okay, some repeated trig identities, but we got there. All right, so we found the area by using Green's theorem in reverse. So you can use it both ways. Okay. So it's a very useful theorem. I want to point out one other thing. I'm not going to do a whole example, but I want to point out that this, I saw an example in the book, and I think there's one like this in the homework that I just want to point out. There's a video that steps you through it, so I'm going to refer you to the video for the details. But yeah, so one other type of problem you might see, it looks like this. They will ask you to do an integral f dot dr, or they'll write it this other way, p dx plus q dy, right? Those are the same thing, right? We learned that those are the same, two different ways of writing the same thing. And they're going to have a region that looks like this. It has a hole in it. That's an avocado, right? It has a hole in it. Now, Green's theorem doesn't apply to such a region, right? Because this is not simply connected. It has a hole. So this is not simply connected. So are we doomed here? Well, no, because we can actually split this into two different regions that are simply connected. So no need to frown here. We can fix this. Even though this is not simply connected and Green's theorem doesn't apply as it is, we can split this region into two regions. If I cut it right here and cut it right here. Okay, so what I'll first do is do the integral along this curve that comes up this way, down this way, along here, over here, and then back over here. That's curve 1. Okay, then I'll also integrate along curve 2. Curve 2 comes along here, goes here, here, goes the other direction over here, comes up along the top of the hole, and then comes back this way. So curve 2 goes counterclockwise this direction. Now look what happens when I integrate along both those curves. They integrate in opposite directions here and here. So when I do the line integrals, they cancel each other out. So even though I kind of cheated by cutting into the region, I canceled it out by coming back out in the other direction. So in the net result, that part won't matter. So I actually will be able to integrate over this region, provided I cut it like this. So what this is saying is that I can rewrite this as an integral along C1 plus the integral along C2. And now Green's theorem does apply. Green's theorem applies to each one of these individually because each one of these separate regions are simply connected. So we can use Green's theorem individually on each of these. Use Green's theorem on each individually. And that's why we're happy now. So even if the region's not simply connected, you can still do it, provided you can cut it into separate simply connected regions. Okay? And there's an exercise in the homework where you are asked to do exactly this. And there's a video where they step you through it, but I think it's saying exactly the same thing. Okay, so you could probably figure it out without looking at the video based on what we just talked about right here. All right, so that's chapter 6. I just wanted to run through everything again. I hope that was helpful. Like I said, well, tomorrow and the day after, we'll just be reviewing. So we can go back and review anything going all the way back. I think we started in chapter 2 in this class. So all the way back to chapter 2. Let me double check. Yep, that's where we just started talking about vectors in the plane. So everything from there, we talked about dot product, cross product, equations of lines and planes, cylindrical and spherical coordinates. Oh, actually, we didn't talk about those until later. Surfaces, we talked about vector valued functions, arc length, work. We talked about tangent planes, finding the tangent plane to a surface, the chain rule in multiple variables. We talked about directional derivatives and gradients, maximum and minimum problems, Lagrange multipliers. Then we did double integrals in rectangular coordinates, polar coordinates. We did triple integrals in cylindrical and spherical coordinates. We computed center of mass. We did change of variables where we computed the Jacobian. And now we're in chapter 6, vector fields, line integrals, conservative, and Green's theorem. Conservative vector fields is a section, but it kind of fits in here. So that's why I didn't say it separately. But yeah, the final covers all of that stuff. So that's a lot of stuff. So I'll try to put together a guide of things maybe you should focus on, okay? And I'll post that and send an email out when I do. Okay, any questions? Make sure you get started on that homework. I've got all the homeworks posted now, so. Okay, good. Okay, so I'm gonna stop the recording anyway. I can find it.